to by Energy Club IIT Bombay. So as we see, as technology is improving nowadays, solar power is becoming more and more viable alternative generation method to fossil fuels. So on this note, I would like to introduce our esteemed speaker for today's session, Professor K.L. Narsimha of Electrical Engineering Department, IIT Bombay. Sir has served as a professor at TIFR in the Department of Condensed Matter Physics and Material Sciences. With over 1700 citations and 140 publications, Sir specializes and holds his research interests in study of photovoltaics and use of organic semiconductors in such devices. Today, Sir is going to enlighten us on solar photovoltaics and dive into the details to give us an idea to how to make it more efficient. And Sir would also shed some light on the current scenario and also the future of solar photovoltaics. Without any further ado, I would ask Professor Narsimha to bestow us with his words.
Okay. Thank you, Mr. Parida. So what I'm going to do today is I'm going to give you some basic idea of what solar cells, the physics of solar cells, essentially. Okay. So this is the plan of my talk. Now, it looks very funny that if you're doing solar cell physics, you're going to shine light, you're interested in power. But it turns out the most important for understanding and for design, the dark IV of the solar cell is very important. And I'm going to show you why that is indeed so. And because many people make this mistake, oh, I have the lighted IV of a cell and I don't have to worry about the dark IV, and nothing can be farther from the truth. Then I will talk a little bit about lighted IV and what determines the open circuit voltage and current voltage characteristics, and then kind of conclusion. Okay. And if you want, you are free to interrupt me in between. And I don't know where to look, but maybe the organizers can prompt me if you have a question. Okay. So first, some basics. The most important thing to understand when you have to make with semiconductors, if you have to do anything, is to be able to draw energy level diagrams, especially when you take two materials in contact and put them together, you have to ask what happens. And for that, the idea of a Fermi level is very important. The Fermi level is like a chemical potential. In equilibrium, the chemical potential everywhere has to be the same. Otherwise, there will be a net flow. For instance, if you have one cylinder of nitrogen and another cylinder of oxygen next to each other, separated by a small hole, even if they are at the same pressure, the nitrogen will flow into the oxygen to mix, and the oxygen will flow into the nitrogen to mix till the concentrations are the same. That's because the chemical potentials are different, and that's the chemical potential. So the Fermi level is the chemical potential and is the driving force, if you like, for drift and diffusion and all these things in semiconductors, for all electron systems. So what I'm going to do in the next few slides is first show you a couple of junctions, how junctions are formed, and then I will take the PN junction as a very special case and tell you why it is so special. Okay? So this is the plan of my talk. Okay. So first, I have here, you can see this thing on red. That's the conduction band of some semiconductor, and it has some Fermi level. I did not draw the valence band, it's somewhere below, it doesn't matter. So this is the Fermi level of the semiconductor, the black line on the right. On the left, I have taken some metal and the Fermi level of a metal, and of course, I have drawn that there, and I have not put them in contact, although they seem to be in contact. They are apart from each other. So within each, the metal Fermi level is in equilibrium itself. The electrons in the semiconductor are in equilibrium with themselves. But if I put it in close contact, so you can look at one important parameter we look is the barrier height, which is the distance from the Fermi level of the metal, which happens to be the highest field level, to the conduction band. So if you want to put electrons from the metal to this conduction band, it has to overcome some barrier, which is called phi b, which is the barrier height. Okay. Now let us see what happens when I actually put them together. So this is how we started off. When I put them in intimate contact, then what these lines that I show here, maybe I should get that pointer more. if you can see this red dot out over here, this is the Fermi level of the metal, and there are lots of electron states above, which is true for all metals. But now when it comes in contact, what has happened is the Fermi level of the metal and the semiconductor have to be constant, and that can happen when I take charge and transfer electrons from the semiconductor to the metal, and every time I make a transfer of charge, the potential energy of the metal will increase, and it will come and this charge transfer will continue till the Fermi levels align. On the semiconductor side, earlier you can see the bands were flat. That means there was no field, there was no potential inside the semiconductor. Now, because of the fact that you have donors, because the N-type semiconductor I have taken, that there is some band bending inside the semiconductor, and these blue dots that I have here are electrons. Okay? So, but the point I'm trying to make here is whenever you take two different systems whose Fermi levels are different and put them together, you always will have a built-in electric field. And that built-in electric field will show up by a potential difference between the left and the right-hand sides of the material. Okay. So now let us see what happens. In equilibrium, I have to. In equilibrium, even if I short circuit it, even though I have an electric field in here, there is no current. The net current has to be zero. And so what does that mean? In practice, there are electrons that jump from the metal into the semiconductor, and that I will call J metal to semiconductor. And the reverse current, J semiconductor to metal, must be exactly equal and opposite, and that is the only way we can have a net zero current in the absence of bias or light when you short circuit this material. Now let's see what happens when I, sorry, I went wrong direction. Let me see what happens when I start biasing it. So this is zero bias, and now when I bias it, you can see that this barrier, which was so large from the semiconductor side, that has become small. But phi b from the metal to the semiconductor remains unaffected, because when I put a negative bias here, the Fermi level of the metal is pulled down by the amount of bias with respect to the semiconductor. So the number of electrons that went from the metal to the semiconductor was exactly the same as before. But now from the semiconductor to the metal, because it's a much smaller barrier height as opposed to here, there are more electrons that will leave the semiconductor and get into the metal. And so I will have a net current in the external circuit. So what will happen is this electron will go like this and come out into the battery, the positive of the battery, and then inside the battery, this energy level will be raised and pushed up. I don't know how do I move this, and moved up into so that the electron is injected back into the conduction band, and that completes the circuit. Okay, so this is how. So if you ask what is the current characteristic, so the current there will be, so we can summarize this by saying that in forward bias, there is a net current flowing in the external circuit, and because of the fact that the number of electrons that will go over this barrier will go as exponential QV by KT, the current will always have this form: J is equal to J naught e to the QV by KT minus 1, and this minus 1 comes because there's always this current is always there from the metal to the semiconductor. So I want to emphasize this, that whenever you have a barrier, it could be an insulator metal, semiconductor metal, PN junction, whatever it is, whenever there's a barrier, the current will always go as e to the QV by KT minus 1. This is a form that you'll have because it's the number of carriers that can overcome this barrier when it goes from right to left. So the physics of this is not in here. The real physics of this is in the prefactor, J naught. Because let's say there are a number of electrons here above this barrier is e to the QV by KT, e to the minus QV by KT, and then these electrons will come to the surface. Some of it will get reflected and come back. Some will be able to make it through depending upon what the density of states here. And that is what determines J naught. So all the physics of transport is in J naught and not in e to the QV by KT. This is just an injection term. I want to emphasize this. And maybe there is, yeah. So the exponential factor is just injection. The pre-factor, that is J naught, determines the mechanism and the current at a given voltage. Because e to the QV by KT will be the same whenever you have a barrier. That's just a fixed number at a given voltage. But J naught can change from material to material. Okay. Yeah. So that's what it says. All the physics is in J naught. Now, I want to go over from a metal semiconductor to a PN junction. That this is what happens when you have a semiconductor junction. So let's consider the situation. I have an N-type semiconductor, which I have shown here. So N-type semiconductor has more electrons, and the Fermi level of the N-type is very close to the conduction band. I have a P-type semiconductor here, and the Fermi level is close to the valence band. There are more holes and fewer electrons. Now, what will happen if I put this N-type and P-type semiconductor together? If I put it together, the rule is the Fermi levels must be the same. That means that will happen if electrons go from here to here, then this becomes positively charged and this will become negatively charged. And so the electrostatic potential of this will be raised and this transfer will take place till the two Fermi levels align. And that will happen in a situation like this. Okay, so this is P and this is N, and then when the Fermi levels align, again, like in the previous case, there's a barrier built up between the two P type and the N type, just as it happened in the metal semiconductor case. So again, although I have an electric field inside, if I short circuit this, there is no current because the number of electrons that will go from right to left will be some J naught, it will be the same as the number of electrons that can roll down. There are electrons on the P side, but smaller in number, but they can roll down the barrier hill. And so this is a drift current and this is a diffusion current because this is driven by diffusion. And so this has to balance out for electrons and holes separately. Okay, and that is why I will have a net current. Now let us see. Okay, so I'll just put in some numbers for you. Now let us see what happens when I. So here again, this is at zero bias. This is what we had, and now let me put a positive bias on the P. If I put a positive bias on the P, electrostatically the whole P is pulled down by the amount of bias. So this is the Fermi level of the P and this is the Fermi level of the N, and the difference between the Fermi levels is the applied voltage. Now see what happens. Here, the electrons that went from N to the P faced a large barrier, and when you applied forward bias, this barrier is reduced, so you'll have more current and then exponential QV by KT current, which will go from the right to the left. On the other hand, those electrons that were here and that roll down, they can continue to roll down, and so there is this term -1. So the current again is given by J naught e to the QV by KT -1, and I want to emphasize, whenever you have a barrier, the current will go as e to the QV by KT, and this is just called an injection term, and J naught is where all the transport business is, and we will spend the next two slides looking at J naught. There is one important difference between, unfortunately, I don't see people's faces, so if you have any questions, please alert me so that we don't have to take questions only at the end. It can also be done here. So the other thing I want to mention is, this what is different from the metal semiconductor junction is, this is P-type and this is N-type. When you apply forward bias, electrons go from the N side to the P side. So and these become minority carriers because in the P-type, the most of the carriers are given by holes, and so this is a minority carrier. Similarly, holes will go from P to N, and where they become minority carriers. So the PN junction is actually a minority carrier device. I want you to please understand this. It's a very important thing, and not many times is not fully appreciated. And this is different from what happened at the metal semiconductor. The electrons went in the metal also. They were electrons, so that was a majority carrier device. Here, when it comes to the P side, the charges that come are electrons, and these electrons are minority carriers. Okay, so what you have is injection is minority carrier injection. Okay, so again to summarize, get rid of. Oh, sorry. So to summarize, I think I went. So you have J is J naught e to the QE by KT minus 1. This is just an injection term. And now we are going to see what determines J naught for a PN junction. And those of you who are working with organics, with perovskites, they are all, for all of them, you know, your organic solar cell or a perovskite solar cell, you will have a whole transport layer, an electron transport layer, and the perovskite is sandwiched between that. Same is true for the organic. So they look like PIN devices. So what I'm going to say is quite important for that. Okay. So now let us see what happens. So there is a now, whenever you have a PN junction is a very special case of something called selective contacts. Those of you who are working in perovskites and organics, you will call this HTL and ETL, just to make it connect, make the connection for you. And I will show you why that is important in the next slide. What this means is when you have selective contacts, is different from the metal semiconductor case. The metal semiconductor case, the electrons went. Let me just go back. The electrons went from the semiconductor into the metal. There was no problem with it. There was no barrier for that. But in the case of selective contacts, in the case of selective contacts, electrons, this contact can only extract holes. So electrons cannot leave the P type from the conduction band. Let me go to the next slide. That comes out more easily here. If you inject electrons, the electrons cannot. So the rule is, in the P side, the electrons cannot leave from the conduction band. Only electrons can leave from the valence band. If an electron leaves from the valence band of the silicon into the metal, that is called hole injection because this electron will leave behind a hole. And that is why it's called a HTL or hole injecting contact. Okay. Similarly, on the N side, electrons can leave from the conduction band, but the holes cannot leave the material from the valence band. Only electrons can leave. And this is very important for you. And this is the principle of something called selective contacts. And PN junction is a very special case of the selective contact. Let me explain to you what this means. So that means by forward bias, this is just all dark. I have applied forward bias, electrons from the N went into the P where they are minority carriers. Now these electrons just cannot go to out in the external circuit to make a current. The only way they can go is this electron has to recombine with a hole. And of course, so then this hole is filled up with the electron. This electron can get out in the external circuit like this, and then in the battery, it will be raised to a potential, to the negative potential of the battery, and injected back into the N-type to complete the circuit, to make a complete circuit. And this is very important because what this says is the current is only a recombination current. J naught, this is J naught for you. J naught is a recombination current. So the current you can control by controlling the number of recombination events. So J naught is, so if you ask how many recombination events are there, it is just J naught divided by Q. That's the total number of recombination events that you actually have in here. And so the recombination rate, which is given by 1 by tau, where tau is this lifetime of this carrier. If the carrier has very large lifetime and does not recombine, then tau is going to be very large, and then J naught will be small because the number of recombination events will become very small. So tau, which is the lifetime of this excess carrier, it determines J naught. That means I can control J naught by controlling the lifetime of this excess carrier in the semiconductor. This is the operational point which I want to actually say. The dark current is all recombination current. If you want to reduce the number of recombinations by making this lifetime very large, and we'll see what determines the lifetime in a minute, then your J naught will change. So your J naught can change depending upon the lifetime of the excess carrier. Okay. So this is the message I want you to take away. In the PN junction, our current is a recombination current. And the recombination current, every time an electron recombines with a hole, an electron flows in the external circuit. And this is the second approach. Every time an electron recombines with a hole, the current flows in the external circuit. Similarly, if an electron recombines with a hole here, the current flows in the external circuit. Okay? So, and every recombination event gives rise to 1 unit of dark current. Okay. All right, I have said this. So you can write J naught really as something A by tau, where A is some fixed quantity. Large tau means small J naught. And you will see that in design of solar cells, you want large lifetime, has to be as large as possible, which means you minimize J naught because that gives you the highest open circuit voltage, and you will see that in a minute. Okay, now how am I doing for time? Okay, I have 20 minutes in, so I'm all right. So I'd like to finish in 40 minutes. So if you look at a real diode, the electrons, we said, will recombine here in the bulk. It can also recombine in the junction region, in the depletion region. Whenever it recombines in the depletion region, the current will go as e to the qv by 2 kt. In general, the current is written as J naught e to the qv by n kt, and n can go from 1 to 2. And what this means is, if n is equal to 2, that means all the recombination is taking place in the junction if you are at low injection conditions. And if n equal to 1, the recombination is taking place in the bulk of the material. So n, the ideality factor, tells you spatially where the recombination is taking place. Okay, I must, however, qualify this by saying at high injection, n will always be equal to 2, even if there is recombination in the junction. Okay. So that is the story of J naught. So we said J naught determines the number of recombination events, and by looking at the ideality factor, by knowing what the ideality factor is, you know whether it's recombining in the junction or in the bulk of the material. I think that's amazing that you know where it is recombining by just looking at some number. Okay, so now we have to ask ourselves, what determines the lifetime, the excess carrier lifetime? So the recombination rate is given by dn by dt minus dn by dt, because you're losing carriers. So it's minus delta n, which is the excess carrier density, divided by the lifetime. So what is the life? So the effective life. So there are at least two ways by which recombinations can take place. One is radiative, that this electron and hole recombine and give rise to light, and that is called radiative lifetime, and that is the largest lifetime possible in any given system. You cannot do better than that. And it's the aim of all solar cell people to make your effective lifetime equal to the radiative lifetime. However, I can also go, so this is an example of the radiative lifetime. The electron and hole recombine and give rise to a photon. Alternatively, I can have centers in the mid gap. The electron is captured here and then it emits And here, and this is a non-radiative event, and so this is an example of a non-radiative event. And you can easily ask how much is this non-radiative lifetime. So 1 by tau r is the probability of capture by this defect multiplied by the number of defects multiplied by some velocity. So what this means is that the non-radiative lifetime is controlled by the number of defects that you have inside the sample. And so if you make your sample better and better, this part of the non-radiative lifetime can go away. There is another non-radiative lifetime which is called OJ recombination, which is fundamental and cannot be gone away, important at high carrier densities, and I will not worry about it just now. Okay. And now here is a statement that I will make. At low injection, if it's a high quality material, the effective lifetime of the excess carrier will be only radiative because there are no defects. And this is easy to accomplish in direct bandgap semiconductors. In indirect bandgap semiconductors, the radiative lifetime, like in silicon, it can be, I don't know, depending upon the, I will give you a number a little later. So usually the effective lifetime is controlled by the number of defects that you have inside the system. Okay, so here is some number. If you have a background doping density of 10 to the 15 per centimeter cube, for a direct band gap material, the radiative lifetime is 10 microsecond, but it is 1 second for an indirect band gap material. That means this carrier can live as long as 1 second if the doping concentration is 10 to the 15. So if this is much smaller, then of course all the recombination will take place through this channel and not through this channel. So if you assume 10 to the 12 defects per centimeter cube, that tau nr, that was this channel, becomes 10 microsecond. So you can see if you have an indirect bandgap material, if it takes 1 second, if the electron is to recombine radiatively, if it is going to take 1 second and only 10 microseconds through defects, all the traffic will be through defects. And so in indirect bandgap materials, controlling these defects become extremely important. Okay? Okay. So that is, so I just want to again say that J naught is a measure of the number of recombination events that you have. And you can see why this is important. You know, if you have a solar cell and you put in extra carriers by light, you want those carriers to go out into the external circuit and not recombine. If you recombine, you lose those carriers. So you want the lifetime to be as large as possible. So you want J naught to be as small as possible. And that is why and you can measure J naught directly in a dark IV measurement. Okay, real cells, if you take silicon cells, they are large area, 6 inch by 6 inch, 15 centimeter by 15 centimeters. So you have non-ideal diodes, so you have shunt resistances. So what you will have, and many of you, I'm going to give this example because those of you who are in the lab doing experiments, there is something for you here. So you may show dark IV like this. However, when you plot it in log scale, you see the current has this shape. So it's always important to plot the current on a semi-log, a log current versus voltage. And you will see why this is so. So now what I'm going to do is blow up this region here, the negative region and a small forward bias region. And you see, this is linear. Linear means if the IV is linear, it is like a resistor. So there's a resistor in parallel with the diode, and that is called a shunt. So that means up to 0.2 EV or 0.25 EV, all the current is going through the resistor, nothing is going through the diode. And that means on this characteristic, till about this current, all of it is really going through this resistor, as given by this value. Okay, so if you, many times, if you do thin films, this is a big problem. And so it is important to subtract off this component of resistance so that you can see what a true IV looks like. Otherwise, it's very frustrating if you are actually doing this. Now, what I'm doing is I'm taking this data from point 4 to point 5 eV, that is in this part of the curve, and you can see that if you plot this, this has an ideality factor of 2, and that means this part of the current is dominated, all of it is going through those defects and not through the. However, if I go to a much larger bias, that has goes as n is about 1.1 or 1.2, which is close to 1. So your IV actually looks like, if you get away from the region where the shunts dominate the current, here you have n equal to 2, and here you have n equal to 1. So you can see, so this is the region where all the recombination takes place in the junction, because you have lots of defects in the junction, and this is the recombination in the bulk. And it is the purpose of everybody to reduce this as much as possible so that the IV looks like this and not like this. Okay. Okay, so let me summarize. N equal to 2 means the recombination takes place in the junction. N equal to 1 means recombination takes place in the bulk. And J naught is a measure of how many high density materials. N is equal to 2 can happen in the bulk. This is a consequence of high injection condition. And if somebody is interested, I won't spend time on that, but I can go over it if somebody is interested. Reasonably on time. So J is J naught e to the QE. So whenever you have a barrier, current will be in this form, and all the physics is in J naught. And for a selective contacts, J naught is the number of recombination events that actually takes place. At low voltage, shunts can dominate the current and not the diode. So most of the current goes through the shunt. So there's no physics in that of the diode. And this is the general equation for a current voltage relation for diode. Okay. So why is the dark IV important? It gives you information of J naught, and that means I know how many recombination events I have, and by looking at n equal to 1 and n equal to 2, I can tell you where the recombination is taking place in space in the junction. We know there are shunt paths. I have not talked of series resistance. This is something that also exists, and you can get all of these information from the dark IV characteristics. Okay. So maybe I can stop at this point and ask if there are any questions. Parida, what would you want me to do? Ask questions, take questions at the end, or take questions now? Hello?
So I would suggest we can take the questions at the end. Like as of now, there are not much questions raised, so maybe we
All
can
right,
take it at
good.
the end.
All right, very good. So now let's go over to what happens under illumination. So this was our picture, if you remember, of the dark. When you took the P and N, put it together, we had a picture like this, and this is what happens in the dark. And I said, if you short this, you get no current, because the number of electrons that go from the right to the left is equal to the number of electrons that go from the left to the right. Now, let me still short this, but I shine light. If I shine light, I'm going to create, so this is the P side, and the P side has very few minority carriers. It has lots of majority carriers, lots of holes and few electrons. N side has lots of electrons and few holes. So when I shine light, let me just look at the electrons, and whatever I say for electrons is valid for holes. Let me create. The advantage with light is, here I have schematically shown 3 electrons. When I shine light, I can increase the number of electrons, let us say from so background, let us say there were 10 to the 4 electrons. I can increase it by shining light, I can increase it to 10 to the 10. Okay. Now the doping can be 10 to the 16, so for every electron, if I create a hole, it's 10 to the 16 plus 10 to the 10, so the number of holes has not changed. Okay, so now you see what happens. This current, if I short this, I will get a current, and the current will happen because the current that's this diffusion current is still the same, which is trying to go from right to left, but now the number of carriers has increased tremendously, and so this current will increase. So even under short circuit current, even under short circuit, these carriers will flow, and I will get a current in the external circuit. And this is called the short circuit current. And this is true for electrons on this side, and this is true for holes on this. So electrons will leave from the thing, the holes will leave from this side, and so I will get an external current in the thing which is under short circuit. The thing to note is current is now ulta, it's flowing in reverse bias, because earlier in forward bias, this was how the current was going. You injected it, it recombined and went out. Now it is not like that. Electrons come here, this electron roll down and get into the external circuit. And so this is the ulta direction, and so I have the current is in the fourth quadrant, and this is very important, as I'll show you in a minute. So this is what a typical IV under illumination is. And why is so? You see, this current is in the fourth quadrant. Why is this important? In the first quadrant, both the current and the voltage are positive. Okay, so the power is equal to I times V, and so if it is positive, then that means you are dissipating power. In the third quadrant, both current and voltage are negative. The product is positive, so here also is dissipation. But in the fourth quadrant, voltage is positive, current is negative. So IV product is negative, so I have generation. So this is why a solar cell is a power generator. Okay? And there are, for this talk, I am going to focus only on two parts of the cell. One is at short circuit, which we already just saw. We have at short circuit, there's a current that flows. And then if you break open the circuit, then of course there's no current flow, but then it will generate a voltage. The solar cell will generate a voltage, and that is called open circuit voltage. And while these two are important, current times voltage here is zero because V is zero. Voltage times current here is zero because current is zero. So you don't generate power at short circuit current or at open circuit voltage. You generate where IV gets maximum, and this is called the maximum power point. And this is we call maximum voltage and maximum current. So I times maximum MPP multiplied by VMPP is actually my power that I can generate and give to the external load. Okay, so I just showed you a cell which is a dark IV and a lighted IV. Dark IV is the first quadrant, lighted IV is in the fourth quadrant. Now, I want to spend the next few minutes asking what determines VOC. Now, the thing is, when I shine light, let me go back to this slide. When I shine light, irrespective of voltage, this current will always get generated, the short circuit current light. So, I can write, oh, I'm sorry, I'm going the wrong direction. So, I can write at any given voltage, the current is a constant current due to the short circuit current, and then when I apply voltage, the dark current will flow. So, the total current at any given voltage is minus JL plus J dark, which means this. So minus JL, which is this quantity at short circuit current, and then if I apply forward voltage, the dark current will flow. So the total current is the sum of the dark current and this light generated current. And this is a very important principle called principle of superposition. At open circuit voltage, my J is zero by definition because I've opened it up so no current can flow. So that will happen when J dark is equal to JL. And that means at open circuit voltage, the current cannot flow out. All the light generated carriers can disappear only by recombination. So if you write down J is equal to dark is J naught exponential Q, the V is equal to Q VOC NKT and equal to JL, you find VOC is given by KT by Q, but this is the point. JL by J or naught. J naught determines the magnitude of VOC. The smaller the J naught, the larger the VOC. And that is why it's important to get your J naught down to very small values. And that you can understand from the doc. So there's another way of looking at this. Sorry. And that is, so I won't go through the derivation, but I will say the same formula which we used here, I can recast this into assuming that, supposing I did not have any defects, then the maximum VOC will be that J naught which only had the recombination through radiative events. So you can generally write VOC measured is this plus log of eta PL, because when the electron and hole recombine, they have to give light. And if only radiative recombination is allowed, then every recombination event gives light, and then the effective tau is equal to tau r, and so the efficiency of photoluminescence, that means one recombination event is one photon out, so this becomes 1 and log 1 is 0, and that is the maximum open circuit voltage you can hope to get. And that happens when tau is equal to tau r, when the lifetime is equal to the radiative lifetime. So in practice, of course, your lifetime is the sum of 1 by tau r plus 1 by tau nr. So reducing this, and that means reducing J naught, is crucial to getting a high VOC, and high VOC comes when tau equal to tau r. What this means is a funny result. A good solar cell is a good LED. This sounds counterintuitive. You shine light, and at open circuit, if you can get every recombination event only radiative, then that will have the smallest J naught, and so you will get the highest open circuit voltage. And you will see this in this example here. If you take a typical commercial silicon cell, they have lifetime. I told you at the tau r can be close to 1 second. So tau f, if it is only 50 microsecond, open circuit voltage are 630 millivolt. Some advanced technologies have open circuit voltage like 740 millivolt, and all of that is accomplished because tau NR has decreased, or tau lifetime has actually increased. So increasing lifetime and making it equal to tau r is the secret to making high open circuit voltage solar cells. Okay. Now I'm going to talk about the short circuit current. What determines the short circuit current? So you go back to the slide. You know, I shine light. I create these excess minority carriers. Now, or let me look at it from the whole. It's the same. Don't have this arrow here, so I will look at it on the N side. So I shine light. I create excess holes. Now, if all these holes can move out of the external circuit, and that means there is no recombination in the N side, I will get the maximum current. So the short circuit current is the generation minus the recombination. Because the current is negative, I have put R minus G. Okay. So if R goes to 0, then that means the current is just minus QG, which is the number of holes that I have generated and the number of electrons that I have generated. Okay? And the short circuit current is reduced by recombination, again by that, with the same thing which limits J naught. So that is why J naught is so important. So, and recombination means delta N by tau, so making tau as large as possible is what will make this will reduce. So low recombination requires small J naught. So, you know, for voltage, you require a small J naught. For good current, you require small J naught. So, J naught is very, very important. And this shows up like L squared is diffusion length is some d tau. And I will say it slightly differently. So, good collection, the diffusion length must be much larger than the thickness of the cell. That means no recombination will take place. before. And then I will. This is just to show you one of the super record silicon solar cells, which some 26% or so was made with 740 millivolt and 40 to 43 milliampere of current. Okay. These days in the literature, I mean, it is very sad for me to show that even the dark heavy is in the fourth quadrant, the lighter heavy in the first quadrant. Sab ulta hai. This is because many chemists started doing it and unko farak nahi pada ki whether fourth quadrant lighter IV has to be there or dark IV. And so people make software of this kind. So please don't get confused by such software. Okay? Okay. So, so in a solar cell, the most important parameter is the mu tau product. Mu is the mobility and tau is the excess carrier lifetime. Diffusion length is just mu tau multiplied by kT by Q, and drift cells is just mu tau into some built-in field. So mu tau is what is important. So you have to maximize mu tau, especially in the thin film solar cell, like many of you may be doing. Thin film solar cells, please maximize mu tau, and that is the secret of success. Okay, so I conclude. I am now. Okay, I'm on time, little more time. In the PN junction, the selective contacts, that means you have HTL, ETL, so that the dark current is decided by the excess carrier lifetime, and the number of recombination events is just J naught by Q. So we have to reduce recombination, which means reduce J naught. So dark characteristics are very important, and open circuit voltage is limited by non-radiative recombination. And for good current, you should have large mu tau. I think with that I will stop. Sorry, I took 5 minutes more. Oh, but I started at 5:05, so that was all right. So thank you for your attention.
Thanks a lot, sir. So now, so in the talk. So the first doubt goes like this. So Yash asked this doubt as on a material to material basis. So how do we, have the traditional semiconductor materials which we use fare against the modern organic polymers which we use right now? So does the material used in the resistor cause about fluctuations in the output current or something like that?
No, okay. Just repeat it. I didn't get the full question.
So on a material to material basis, how have traditional semiconductor materials fared against the modern organic polymers?
Okay. So let me take that question first. So you have different absorbers. You can have silicon, which has been the workhorse for many years, but you can have different absorbers. You have cadmium telluride based solar cells, which are not single crystal, which are multi-crystalline cells. Then you have organics, which are amorphous. Then you have perovskites. So many of these are thin film solar cells. Okay, and so what is in order to get the full, if you want to get the current, depends upon the number of carriers I can generate, and that means I must have. So the band gap is actually important for determining what the current actually is, because then the smaller the band gap, the more carriers I can generate, but then the voltage will become much smaller. So there is an optimum of band gap that you can have so that you can get the highest efficiency, and that is in the vicinity of 1.4 EV or so, 1.3 to 1.4 EV. Okay, so does that answer the question or no?
Yeah. So like what exactly he emphasizes on is uh, like we have the silicon which is the traditional material which we have been using. So right
Yeah.
now we have the organic material which have been introduced. So
Yeah.
do they have the capability enough to to replace the silicon traditional way which we're using?
Okay, so this is a very good question. So what is very important is technology. Now, silicon has had this advantage that its technology started in 1954, the first solar cells that were made, and it has it's a 65-year-old technology which has been continuously upgrading itself, making it pure, 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 pure. Now, there are thin film cells like indium, gallium, I'm sorry, um, indium, gallium, selenide, and such materials where cadmium, not gallium. So, where you have, they are essential. So, what happens is the lifetime is not large in these materials, and the important thing to do then is to make the thickness small so that mu tau times some built-in field is much greater than the thickness. Amorphous silicon is another example. Okay, so these are different generation of cells. So now in order to succeed in the market, manufacturability, stability, price, these are important factors. And unless one does the research, one does not know. So let me give you an example of amorphous silicon. Amorphous silicon was very heavily researched from 1977 till about 2016 or so. And people knew how to mass manufacture these cells. But ultimately, it did not succeed because its efficiency was limited to some 13-14% and could not compete with crystalline silicon because of investments in technology drove the price down to make it to put other people out of the market. So now new materials come, and when a new material comes, if its stability is good, it's like perovskite. It's been stupendous, 22%, and no other material has gone this rapid in such a small time, gone to such high efficiency. But now, making it on large scale, looking at the stability, looking at encapsulation, all of these become important. However, we must not forget, we only think of solar cells in terms of power for our house and industrial lighting and things like that. But there are many applications which don't need that. For instance, if you have a smartphone and you want to keep your battery trickle charged all the time, if you can make a small solar cell which will work in room lighting because you can choose molecules which are right, then there's an application which silicon cannot compete with because it is bendable, it is flexible, you can fold it, etc. So so there will be niche markets for some of these things. At this point in time, it looks difficult. It's always difficult to predict the future, but at this point in time, it looks difficult to believe that for power production, silicon will be easily replaced.
Right. So there's another question from Yash. She says that the material used in the resistor. So does that cause any fluctuation in the output current?
What do you mean by material used in the resistor? Yash, can you please clarify what do you mean material used in the resistor? What does that mean? What resistor? Which resistor are you talking about? Maybe he has to
So
unmute himself and ask.
yeah, so until the time he gets to raise his point, we'll take another question till then.
Ah,
So Abhik Bhattacharjee says, so the current flow in the solar cell is drift dominated. So he says so current flow in a solar cell is drift dominant. So is that true according
no.
to him?
Well, no, it depends on the solar cell. For instance, if you look at silicon, you have a large cell and light. If you look at long wavelengths, because an indirect bandgap semiconductor, alpha is very small, the absorption coefficient is very small. So if you look at something of the order of 950,000 nanometer, 1050 nanometer, the light generates carriers at the back of the cell and there is no drift. It has to only come to the front by diffusion. So in cells like silicon, which are indirect bandgap materials, they are diffusion dominated, and the only way to make it drift dominated is to make it very thin. When you make it very thin, such that the electric field, the thickness is just equal to the depletion layer, then it will be drift dominated. Because then all the light is generated in the diffusion, in the depletion layer, and the carriers are collected in the external circuit. Then it is drift dominated. But in a traditional solar cell, but then that makes it very thin. Make it very thin. The absorption, the number of alpha is the number of photons that don't get absorbed become very large, and so the efficient. So then and so there is a problem. So either you must have high absorption coefficient, and then you can make it drift dominated. But if you have low absorption coefficients, if you have indirect band gap materials, then they are you have good quality material, they are diffusion dominant. So there's no one answer. It depends on the material and its properties.
Yes. So, moving ahead, Vandana Vinayak says that how do we determine the power efficiency of a solar cell? Like, what are the factors which determine that, and is there any mathematical, stuff to it?
Well, there is no real mathematical stuff. So what you power efficiency means the power output divided by um, I thought I had two slides. Ah. The power efficiency means the power generated by the cell divided by the incident power. The incident power in this case is the sun, which is 100 milliwatt per centimeter square. And now you say, so what you do is you ask what is the maximum power this can generate. So if you what you do is you take this curve, lighted IV curve, and you multiply every point by I times V. Here I times V is 0, and then, but here, because V is 0, and as you go up this curve, your I times V will keep increasing, and then when you go here, your I times V is 0 again, and then as you go down this curve, it will increase, and then there will be some point which is the maximum, and this is the maximum power point. Okay,
Right.
so your efficiency is just this is the maximum power you can get is I times MPP multiplied by V MPP divided by 100 milliwatt per centimeter square. That's all the mathematics that is really involved. Sometimes this is done by calling it a fill factor. They say, the best you can do is you can have, if the IV was straight like this and then became vertical, then I times V is ISC into VOC is the maximum power that you can have. But you have a much smaller rectangle, you take the ratio of the two rectangles, that is the fill factor, and then you just use the fill factor as a way of calculating. But really, IMPP into VMPP divided by 100 milliwatt is my, that's all the mathematics.
Brajender Sengar asks that we are adding JSC to the dark force, so it's shifted into the fourth quadrant. So, is such kind of superposition possible in all type of solar cells?
So if something has to develop, generate power, the I product has to be negative. So all things that generate power will be in the fourth quadrant. So it is not that I'm adding. So what I'm actually I'm doing light, the light has produced these carriers. Light has produced these carriers. These carriers then go down on the side, and that is in negative. Okay.
Okay.
And now, when I want to trace the IV, I will apply some voltage, and that voltage is forward voltage to continue on this curve. And then, of course, this current and this current will add to give me this curve. So this curve is just a superposition of the dark IV plus a constant generation rate. This is not always applicable, but this when it is applicable, it's a very powerful tool.
So there's another question by Yash. So he says, how does the lifetime, that is tau r, that could be scaled or understood so as to get the total lifetime of a solar panel, basically?
See, we have to be clear that there are two. What lifetime for different people has different meaning. When I'm talking of the excess carrier lifetime. That's how long is the carrier free before it recombines. The
Yeah.
panel lifetime depends on how much the panel degrades, how when it stops producing power. So these are two different lifetimes.
So basically he asked that, can they be scaled or can they be related?
No, because it depends on what is my failure rate. So for instance, in a real life situation, uh, so panels can degrade due to many reasons. One is, of course, if the cell itself degrades and the lifetime goes down of the excess carrier. But panels also degrade because there are metal grids and this grid comes off, the connecting grid comes off, or the
Right.
metal contact comes off. That's also failure, but has nothing to do with the carrier life. And most of the failure is due to such failures. The silicon usually does not fail so much less.
Yeah.
Most of the failure is due to contacts, rusting, water ingress, which causes oxidation and stuff like that.
So we'll take three more questions. So here's another from Bhumika. She says, "What is the significance of the ideality factor N for a good illumination?
What illumination?
Uh, for good illumination, what is the significance of ideality factor for good illumination?"
I don't know what she means by good illumination because light comes from the sun. And all that I was saying is this ideality factor. So if you look at the dark IV of the curve, and if you are now the dark IV of the curve, there is a so the dark IV of the curve has a region where n is equal to 1, another region where n equal to 2, and I'm not worrying about the shunt because you should be able to cure that. Now, this is my dark IV, and n equal to 2 means all the recombination is taking place in the junction region. So if I can reduce the number of defects in the junction region, then this will not become like this, but this will go like this dotted red line all the way through. And that will improve my fill factor. So that will make my cell more efficient. The efficiency of the cell will go up, and that is also because under low light, if I'm at low light levels, the sun is not always at noon. If the light level is low, then this begins to dominate the IV characteristic, and then of course your efficiency of the cell falls. So what you would like is a cell which just has n equal to 1, but that is easy to say and almost impossible to get. There's perovskites and such things, even small light, if the background doping is very little, then when you shine light, you are in the high injection region, then N is equal to going to be 2 all the time.
Right. So there's another question. So this comes from Vandana. She says, "Is it possible to convert the other frequencies of the electromagnetic spectrum to the band gap frequency of a solar cell? So like this could boost its efficiency."
Okay, so obviously you want to convert the part that is not absorbed. So I don't know how you will actually do that except by 2-photon absorption, but for that you require very high intensities. Or, and this is what is normally done, is to take two different solar cells with two different band gaps. One is the large band gap to absorb all the blue light and green light, and another, the smaller band gap, is connected in series. These are called tandems, and then that one will absorb the lower efficiency, a lower energy spectrum, and then of the current has to be the same. You have to design it such that the current is the same through both the cells, but the voltages add up, and you can actually get. So the cells which are 40% efficient, 45% efficient cells are made up of 3 or 4 cells which are spectrum splitting band gap. So they have 4 different materials all grown one on top of each other, and the voltages add, and that's where you get a large amount of the efficiency gain. So you get to 43%, 44% in tandem cells.
So here we go with a concluding question. So according to you, sir, what are the current innovations in the field of solar photovoltaics and where the solar technology is heading now.
Okay, so this is a very good question to ask. So let us see where we are. So I think there are some very interesting things that have happened. So I saw a report that for the month of April in England, all electricity generated came from renewables. That means gas and coal plants did not fire at all. It all came from sun, wind, things like this, from renewables. So I think what one is going to see is certainly there is, if we look at trends as they are falling today, I certainly think that solar is going to play a bigger and bigger role because of worries of climate change and fossil fuels and everything. Okay. And the more important part, the costs are falling quite dramatically. Yeah? So I remember that in 1980, uh, one peak watt was $4, and today it is $0.2. So this was almost unimaginable uh, in the 80s and 90s. So, and this all has been possible because of efficiencies of scale of silicon manufacture and making solar cells of high efficiency. So, I think from the point of view of energy landscape, renewables are going to have a large part to play, and solar photovoltaics certainly has a very large role to play. Huh? So there has been this scenario that people were saying the problem is, of course, the sun shines only in the day and does not shine at night. And there I heard this interesting scenario from somebody. He said, well, the sun is shining somewhere in the world throughout the day and night. If it is night for you, it is day there. So if we have a grid that when it is night for you, he will supply, and when your day for you and his night, you will supply, then of course that would be a great way to solve this storage problem. So biggest challenge for solar is actually storage, and increasingly this is where a large amount of research will go in because there are different kinds of storage. You can lift water above and then make it fall down again and run a turbine and generate electricity, but it's very inefficient. Then you can use batteries. And so there's a lot of investment in battery technologies currently taking place to be able to store energy. And maybe one needs just more innovative ways of storing. Maybe you convert it into heat and extract heat out later. So the storage, if you ask me, is going to, because that determines your cost also.
Right.
It's not only generation but also storage. So storage plays a very important role. So I will see not directly photovoltaics but photovoltaic technology. Where storage is an integral part of the technology, playing a very important role. And of course, there will be surprises. Perovskites came out of nowhere. So there will be material surprises, and I think we have to keep our eyes open, just do research, understand more, and see what that you can also be a contributor to that surprise.
Right. So, sir, with this, thank you for your valuable time. So, there were people asking for, certain books for or certain online material which they could actually refer to get a depth knowledge about solar photovoltaics. So, what would you suggest for the same?
Yeah. So one very good website is pveducation.org. pveducation.org. That's a very
Okay.
good, if you just Google PV education, I mean, unfortunately, it is focused on silicon. So if you want anything about silicon, PV education is a very, very good place to start. Okay. And then, of course, for the stuff like organic perovskites, there are only review articles which are periodically published, and one just has to live on those review articles.
Right.
But the general concepts, I will say, this book, there are many excellent books given apart from pveducation.org. There is this book by Fonash, which is very good. It's a little difficult to read, but has all the concepts very clearly explained. Then there is a book by Bube, which is a simpler book. So I would actually take Bube's book first to read before reading Fonash, the Solar Cells by Bube, B-U-B-E. And if somebody wants, you can email me and I can put together a list and send it across.
Thank you, sir. Thank you for your valuable time. With this, we'll end this session for today. Thanks a lot, sir.
Okay, thank you. How do I leave? There must be something to make me leave, no?
Yeah, okay. You can just close the screen share and there you will get a leave
Oh,
option.
close the screen scale. All right. Yeah, no, thank you.
Thank you, sir.